Welcome back to the video on powder metallurgy part 2. Today, we'll explore about compaction and sintering. Compaction is where blended powder is pressed into a solid green compact, achieving density and shape. The high pressure during compaction improves particle contact, allowing better bonding in the sintering phase. Proper compaction is crucial to ensure part strength, dimensional accuracy, and durability before sintering. Types of compaction processes. Cold pressing occurs at room temperature and is commonly used for parts where high density is an essential. Pressure range, typically between 100 to 1000 MPa, depending on the material. Applications, automotive parts and industrial components. Advantages. This method is cost-effective and suitable for a wide range of metals and alloys. Hot pressing applies both heat and pressure, improving bonding for higher density. Temperature, generally 600 to 1000 degrees Celsius. Applications, used in high-strength, high-density parts needed in aerospace and automotive industries. Advantages. Minimizes porosity and enhances mechanical properties, especially useful for refractory metals and ceramics. Key compaction tools include presses. Mechanical presses use consistent pressure for smaller parts, while hydraulic presses offer adjustable pressure for larger or complex shapes. Dies. Made from hardened steel or carbide, dies must withstand high pressures without deforming to maintain part accuracy. Punches. Upper and lower punches compress the powder evenly, creating uniform density. Floating dies may reduce friction during ejection, helping to prevent defects. Several parameters influence compaction outcomes. Compaction pressure. Pressure must be high enough to bond particles, but not so high that it breaks them. Compaction speed. Faster compaction can create density inconsistencies. Slower compaction improves uniformity. Tool alignment. Misaligned tools can lead to uneven density, affecting mechanical properties and possibly causing warping during sintering. During compaction, defects such as density variation, cracks, and springback can arise. Density variation, caused by inconsistent pressure or uneven powder distribution, potentially leading to weak spots. Solution. Applying uniform pressure and precision in die design help avoid these issues. Cracks and fractures often result from excessive pressure or insufficient binder content. Solution. Adjusting pressure settings and ensuring adequate binder prevents these cracks. Springback refers to the slight rebound of compacted powder after pressure release, leading to minor dimensional changes. Solution. Increasing compaction pressure or performing post-compaction repressing can mitigate this effect. Compacted powders have extensive applications in industries requiring precision and strength. Automotive, gears, camshafts, and connecting rods rely on powder metallurgy for consistent mechanical properties. Aerospace, lightweight, high-strength components made from compacted powders are vital for structural applications. Medical, biocompatible implants, such as joint replacements, are formed from compacted powders for precise dimensions and durability. Sintering is the heat treatment stage following compaction in powder metallurgy. During this process, the green compact is heated below its melting point, allowing particles to bond via diffusion. This step strengthens the component, increases density, and enhances mechanical properties. Through controlled heating, internal voids are reduced, resulting in a solid, cohesive part with the required strength and durability for industrial applications. Stages of sintering process. In the initial stage of sintering, the green compact is gradually heated, causing powder particles to begin forming necks at contact points. Key mechanism: surface diffusion. where material moves from the particle surface to create bridges between particles. This stage results in minor bonding with slight densification and minimal shrinkage, setting the foundation for further bonding and densification. As sintering progresses, the intermediate stage begins, where neck growth continues and pores within the compact become interconnected. Key mechanisms: volume diffusion and grain boundary diffusion, where atoms migrate from the particle centers to the necks, reducing pore size and increasing density. This stage is essential for enhancing part strength and reducing porosity. In the final stage of sintering, remaining porosity is minimized as pores close or reduce significantly. Key mechanisms: grain boundary migration and bulk diffusion, allowing for near-complete densification. This stage results in maximum part strength and dimension stability, ensuring the final product meets performance and durability standards. Types of sintering process. Solid-state sintering occurs at temperatures below the melting point, where atomic diffusion bonds particles without liquefying them. Applications. This method is ideal for metals with high melting points, like tungsten and molybdenum, where strong, durable components are essential. Liquid phase sintering involves adding a secondary component with a lower melting point, creating a liquid phase during sintering. This liquid enhances particle bonding. Applications: commonly used for hard materials like tungsten carbide, where binders like cobalt melt to improve cohesion and strength in abrasive or high-strength applications. Hot isostatic pressing, HIP, applies high-pressure gas, usually argon, within a sealed chamber as the component heats. The uniform pressure increases density, eliminates porosity, and enhances mechanical properties. Applications: HIP is popular in aerospace and medical fields for components requiring high density and precision. The sintering atmosphere greatly influences the final product quality. Inert atmospheres, for example, argon, nitrogen, prevent oxidation, ideal for metals like titanium. Reducing atmospheres, for example, hydrogen, carbon monoxide, aid in removing surface oxides, promoting cleaner bonding. Vacuum sintering, conducted in the absence of oxygen, preventing oxidation for reactive materials like titanium. Each atmosphere is chosen based on the material's properties and intended application. Several factors influence the sintering process, impacting the final properties of the material. Temperature and time. Higher temperatures and longer sintering times promote diffusion, enhancing density and bonding strength. However, excessive heat can cause issues like grain growth and warping. Heating rate. A controlled heating rate minimizes thermal stress, reducing the risk of cracks or distortions. Particle size and shape. Smaller particles have larger surface areas, promoting faster diffusion and densification. Irregular shapes also increase contact points, aiding initial bonding. Adjusting these factors ensures optimal mechanical properties in the final component. Common defects can arise during sintering, each requiring specific mitigation methods. Warpage and distortion, often due to uneven heating or excessive temperatures. Solution: careful control of sintering temperature and uniform heating. Pore trapping. Incomplete pore closure reduces strength. Solution: adjusting temperature and sintering duration helps minimize residual porosity. Abnormal grain growth. Excessive heat can cause uneven grain coarsening, impacting mechanical properties. Solution: precision in temperature control and optimized sintering duration address this issue, ensuring consistent material properties. Sintered parts have diverse applications across several industries due to their high density and durability. Automotive. Components like gears, Bearings and bushings benefit from wear resistance and strength provided by sintered materials. Aerospace. Sintered metals with high fatigue resistance are crucial for turbine blades and structural parts, providing reliable performance under stress. Medical. High-density, biocompatible implants like joint replacements are manufactured via powder metallurgy, ensuring precision and longevity in medical applications. We've reached the end of this video. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.